So you need to continue to put your finger on the screen. Okay, so
yes, I consented and it's recorded.
It's a pleasure to have Roberto Emparan, who will tell us about holographic dwells of black hole evaporation.
Thank you. Thank you for the invitation to come. It's a pleasure to be back here. Last time I was giving a talk at this venue. We were watching in 2D, now it's going to be 3D, and this talk will be going even higher in dimensions. So this is a talk about work that hasn't been published yet. It will appear soon. It's been done in collaboration with Rencontres, Suzuki, Maria Masvich over there, and Way. And well, I usually tell my students that when you give a talk or when you write a paper, you need a story to tell. And here I have a story to tell, and I have history to tell, because the origins of the work that I'm going to be talking about today date back to the 2 decades ago. So it's a fairly old idea. It's simple. I think it was very suggestive. An idea that came up 20 years ago. ADS-CFT was still relatively new. But as you know, ADS-CFT, what it does maps the quantum field dynamics. Yeah, I don't know why this is doing. But so ADS maps the dynamics of a quantum field into the classical gravitational dynamics of the gravitational field inside a bulk ADS spacetime. Okay. So I assume that most of you are familiar with this. It's not working as it should. It's stuck. You got stuck. It's not passing the slides.
Your computer?
I don't know. It's some interference. Can we?
Yes, sure. Noise. Okay, people late will learn anything else.
No, the noise is coming from there. So.
Well, maybe you can close the window.
Is it from there or is it from here? For this question, how they're doing works.
I think it got stuck. The presentation.
If you click on your on your slide, sometimes it just
so yeah. So now I should share.
It's still viewing your screen.
Yes.
Still sharing.
No, but I think it's from outside. Let's wait. Close completely the window, and we can open that one on that side for Eric.
So I think that now it should work. Yes. So now we're. So the idea is that what we have a conformal field theory that's dual to the bulk. And usually when we do ADS-CFT, we consider that the boundary geometry, it's typically flat space-time or a sphere, but it could be anything else. In this work, we can specify in ADS-CFT, we can specify what's the boundary metric. And in particular, we can put at the boundary, we can put a black hole geometry. So when you do that, what you have is that your holographic CFT lives on the geometry of a black hole. This geometry is not dynamical, it's fixed. We'll see how we can get past this point. But in principle, this is something that allows you, it allows you to study the holographic conformal field theory in a black hole background using the dynamics of some classical bulk. So you're mapping the problem of quantum field theory in some curved geometry, you're mapping it into classical dynamics in one more dimension. So what you do is, as I said, you have the conformal field theory on some black hole background, you do it holographically. But what do black holes, or what do quantum fields in the presence of a black hole? Well, you know that the main effect of having quantum field theory in the presence of a black hole is that you get Hawking radiation. So the logic of what I'm saying means that you can map the quantum Hawking radiation of some CFT in some black hole background. You can map it to the classical bulk dynamics of some bulk geometry, classical bulk geometry. So you solve the classical gravitational equations in order to solve this problem. This problem of Hawking radiation, which in general is a problem that's non-trivial, but by mapping it into classical dynamics, you can make it easier. So this idea that's not new. There was already a review almost 10 years ago of how to study thermal field theory, or holographic quantum field theories on curved spacetimes using this technique. If you have any questions, please stop. I don't know whether it's clear to everyone. Now, there's some caveats to this, because we're studying a conformal field theory in a black hole background, but you have to take into account that the holographic quantum field theory, holographic conformal field theory, it's not only a conformal theory, but it's a conformal field theory that when the bulk is classical, this is the limit of infinite n and also infinite coupling. Because quantum field theory is infinitely strongly coupled. You may wonder whether, in this case, we should also expect Hawking radiation. Well, something that the fact that you have thermal effects in the presence of a black hole background, this is independent of the coupling, of the strength of the coupling. So you expect thermal radiation effects for the CFT that lives in this black hole background geometry.
Sorry.
Yes.
What exactly do you mean? Because the standard calculation for Hawking radiation is done using free field.
Yes, but the proof that you have thermal effects that, for instance.
Yeah, just from the linear.
Exactly. Yeah. I mean, you can. I mean, it's a property of having the periodicity of Euclidean time, which is something that will hold independently of the coupling of this.
When you have a conformal free theory there, and there's only one scale in the problem, which is the scale of the horizon. Can you argue that you still have radiation? I guess so. Yeah.
I mean, you can perfectly well. I mean, when you do the calculation for a free field, that's a conformal field.
Okay.
So.
Even the scale of it.
Yeah. So now what we want to do is, well, take this one step further. We want to have the geometry that we have at the boundary, we want to make it dynamical. So we're going to do a version of ADS-CFT that's not the standard one, but it's one that's been used recently quite a bit. So the idea here is that you make the boundary dynamical. How do you make the boundary dynamical in ADS? Well, you replace part of the boundary, or part of it, with some brane, something that's not at asymptotic infinity, but it's some finite distance away from the boundary. It's the boundary of space-time, but now since it's some brane, some domain wall that can move in the bulk, then this boundary is dynamical. And this is what gives rise to the idea of a brane wall holography. Here what you have is that you have this gravitational brane, which is this kind of a domain wall or an end of the brane wall, when the end of the wall brane, as people call it these days. It's a boundary that can fluctuate. And one can show that these fluctuations appear on the brane as gravity that's localized over there. So that's the whole idea of Randall syndrome, that you can have, when you have a brane in ADS, then you have gravity in one less dimension localized on the brane. Now this gravity on the brane, that's still coupled to the rest of the bulk. The coupling to the rest of the bulk is described by a CFT. CFT now, if you want, with a cutoff, because we've cut part of the boundary. But what we have, the effective dynamics of this system is not just the CFT, it's the CFT coupled to this gravity localized on the brane, and both systems are coupled. Here in general, I mean, this Einstein gravity, you have corrections, I'm not going to talk too much about. But the idea is that by solving the classical dynamics of some system, some ADS bulk with a brane, then what you're doing is solving the dynamics of classical gravity coupled to a quantum field theory, and both of them are coupled. You're taking into account fully the back reaction of the CFT. And that's something, solving this problem of solving the back reaction of non-linearly the back reaction of a quantum field theory into some geometry, that's a problem that in general is extremely difficult. We only know how to do it using conventional techniques. We only know how to do it in low dimensions. The only technique that I know of that allows us to deal with the back reaction of the quantum fields non-linearly is holography.
The CFT lives at infinity or lives on your brain?
The CFT lives on the brane.
On the brain, okay.
So your brain, I mean, your bulk has at least part of the boundary is the brane. So that's where the CFT lives. And on that CFT, the CFT is also dynamical, the dynamics of the geometry in the brane, that's the diagram.
And when you put some black hole on the brain, what is preventing it from just collapsing inside the ADS?
We're going to see, that's a large chunk of the total.
So here, IJ are
indices along the brane. So these are not. This is not gravity on the bulk. This is gravity on the brane. All of these indices are indices on the brane. brain, on the boundary, and these are indices on the. Okay. So what we want to do is to put a black hole, that this part of the system describes a black hole, and then this part is going to describe a CFT in the black hole background, and as we were saying, it's going to have thermal effects, Hawking radiation, and the system is going to be coupled. Okay. Now, this is interesting because you know that when you have a black hole that's coupled to radiation, well, the black hole is emitting radiation, radiating, and if there's back reaction, then this radiation is taking energy away from the black hole, and then the black hole evaporates, and this is a dynamical process. And in general, following this process of black hole evaporation through conventional techniques, that's extremely difficult. You can only do it in some very simplified models in low dimensions, which are nice, but they also sometimes oversimplify the problem. So we want also to see whether we can do this in more dimensions. And the nice thing is that in this case, we can have the dynamics, the quantum dynamics of black hole evaporation with back reaction. We're mapping it completely to the classical dynamics of some system in the bulk. And we're going to see what system in the bulk we have. But what we want to have is some black hole at the boundary, some black hole on the brain, and then this living in some higher dimensional bulk. That's going to be our CFT. This is an idea that, as I said, it's a little over 20 years old. We proposed it back then. And of course, at that time, we were younger and naive. And well, I think the basic ideas we're going to see is right, but some of the details are much more subtle than we anticipated back then. Other questions?
It's not clear to me how the gravity on the brain decouples from the gravity in the bulk. Could you explain that?
Well, gravity in the bulk, that's the CFT, so it doesn't decouple. You map, so I'm mapping gravity in the bulk. You know that AD-CFT, what it does is maps the classical gravitational dynamics of the bulk to the quantum dynamics of a CFT in the infinite n limit. So this is, if you want, this is capturing gravity in the bulk. And this is the part of the gravity that's localized at the boundary.
And then you are writing with the same indices, right? IJ indices.
Yes, these are boundary indices.
These are the boundary.
Yeah, because you know that in AD-CFT, the boundary describes all of the gravity in the bulk. So yeah, this is, if you want, gravity in the bulk coupled to the mode that localizes gravity at the boundary. Any other question?
But this mode is on the brain, which is not really at the boundary. It's a bit further in.
Yeah, it's farther in, so the CFT comes with a cutoff. Okay. That's not going to be very important, the cutoff of the CFT. Now, how do we describe this process of black hole evaporation in this model? Well, the idea that we came up with back then was the following. First of all, so this is the brain, this is the bulk. So this would be the asymptotic boundary would be somewhere up here at infinity, but we're cutting it off. So a black hole on the brain, we expect that it's going to have a black hole here on the brain, but it extends into the bulk some distance. And this is a solution, a configuration that's sometimes called a black droplet. Okay. So this is first the setup of a black hole on the brain. What would be radiation? What's radiation in the bulk in AD-CFT? Well, radiation, thermal radiation in AD-CFT, that's some black hole in the bulk. When you have a black hole in the bulk, this looks at the boundary as radiation. And if you have a black hole that's falling into the bulk, it's at some distance up into the bulk, you put it up there somehow. When it falls, then what this describes dually is radiation expanding in your boundary. The dual view is some ball of radiation that's expanding. So we want to have these two things. We want to have the black hole at the boundary, and we also want to have radiation expanding along this radiation expanding along the brain direction, which means that some horizon is moving into the bulk. Is this clear? So in order to combine the two pictures, the two things that I described, what we came up with was just hand waving, drawing pictures. But the idea that we came up with is the following: that the Hawking evaporation of this CFT, which is strongly coupled, would be some black droplet that somehow is sliding off into the bulk. We begin here with this black hole at the boundary. The dual view is this one. So we have a black hole, we have a little halo of radiation, but then we thought, well, this black hole wants to evaporate. It wants to shrink, so the black hole is shrinking, it's sliding off, and then it's moving, part of the horizon is moving inside the bulk. So this is the black hole becoming smaller on the brain, but radiation becoming larger at the brain as well. And then, well, if this continues on and on, the black hole is shrinking, radiation is growing, this bulk over here, this describes some blob of radiation that's expanding, and eventually, well, this would pinch off, and the black hole would fall. So why do how do I maybe try to do that? Yeah. Okay. So, it's feeling. Yeah. Too much. Okay. Yeah. So I should stay away from it. Okay. So we have here that when this slides off, then the black hole has disappeared, and then we have a blob of radiation expanding into the boundary. Okay. And there's something that's quite nice here, that this process, because you can consider that this brain could be a two-sided brain. When you consider it like this, then this looks very much like some horizon that's pinching in the same way that that black strings pinch due to the growth of instability. That's a picture that's very close to Maria's heart. I think it's also interesting. I will say something later.
Normally, the black hole will never leave because when the brain has attention is attracting, so the black hole is stuck to the brain like.
So you're saying that this picture is wrong?
Yeah.
Yes. But let me say, so this problem we were describing with words and everything. It's something that at least it looked like it wouldn't be so unresolved. But solving this problem in 4 or more dimensions, that's very difficult. Okay, because you want to solve a problem of a dynamical gravity in a 5-dimensional bulk, and that's something that 20 years ago it was completely out of the question trying to do this. People didn't know how to do black hole collisions for LIGO back then. Okay? So it was a problem that was too hard. In lower dimensions, we found some exact solutions that were available, but the physics was qualitatively different because when we go into lower dimensions, something's changed. So we could make some progress, but the question remained open for many years. Until at some point, it was understood that this nice picture that I showed you is not quite right. It was proven through numerical work, initially by Pau Figueras and Toby Weisman, collaboration with Jim Lucetti, later has been some more work on this, that there exist static stable black holes, these droplets, there are such droplets, and they stay there, they don't evaporate, they don't slide off the brain. It was also found that somewhat different configurations exist for a conformal field theory in some black hole background where there's no radiation. This is puzzling. These results are puzzling because what you have is that there are hot black holes here. The view from the brain is that you have a black hole that's hot, there's radiation that's hot, but this hot black hole is not radiating to cold infinity. So this was a puzzle, how something that's hot is not radiating to outer cold infinity. Yes.
Is your brain infinite or compact?
It can be infinite or compact. So it can be Poincare or it can be a sphere.
So if it were compact, then it's not so much to the power because.
Well, if the black hole is small, it's very much the same puzzle. If the black hole is large, then I agree.
But eventually it should equilibrate at some time anyway. Not disappear completely.
Well, this is the infinite end limit and infinite coupling, strongly coupled limit.
So this static stable black holes also exist in infinite brain space.
Yes, that's right. Yes. So in fact, they were constructed first for the Poincare for a flat brain. The numerical work is done for that case. For other solutions, well, I will show some of the things that we've done models. So here, what we have is that the CFT, the Hawking radiation, is at infinite end and also at infinite coupling. And what was kind of a guess, there was hints that these two effects, and particularly the infinite coupling, might be something that changes qualitatively the picture from what you get from free Hawking radiation. The infinite coupling can change things. And we're going to see how it changes things and how to interpret it. Even if the whole story is not completely clear, infinite coupling and infinite end make qualitative pictures from the usual idea, which is what we were thinking of first when we came up with this model for classical dual of the black hole evaporation. We were taking intuition from the weakly coupled Hawking calculation. And that was turned out to be wrong. But nevertheless, even if these results, the results by these guys, might seem to kill the idea that there could be a dual description, a classical dual description of black hole evaporation, we thought that this couldn't be the end of the story for a number of reasons. One of them is that, well, there may be also, so there are solutions like this which are stable, but there are other configurations like inhomogeneous horizons over here that would describe excited states of the CFT with other arguments for the existence of this, but people hadn't constructed them. Nobody had done, even if people had found these solutions, nobody had attempted to do a dynamical evolution of a droplet or a dynamical evolution of these black holes. Dynamical evolution is something that's much more complicated. What people solved were static or static configuration or stationary configurations, but doing dynamical evolution in gravity is a much harder problem than finding static solutions.
But so if you believe the picture, how can you justify that they can be stable excited state? What could be a state in equilibrium with a black hole?
We're going to see. Keep this question for later, because this is at the beginning of the story how we got something wrong, and then well, what we're going to see is that well, the story is more complicated, and there's a sense in which we could still be right. Okay. So, because this idea that you can have a black hole in the presence of a radiation that's not evaporating, that's something that's strange. I was never quite comfortable with this. I thought that there must be some way of describing the evaporation of a black hole in this classical holographic one.
There's an example. People who do ABS PCB, they have this black hole flat space boundary, and they use it to mimic some plasma balls. But this is some old stuff on plasma balls. I think people should ask the people who are doing it.
But the plasma ball is at the plasma in the bulk.
It's in the bulk.
Yes.
But that one also doesn't evaporate. I mean, that one also you can argue that the evaporation is.
Well, but in that case, you wouldn't. I mean, that plasma ball, what it describes at the black hole in the confining bottom, what it describes as a plasma ball at the boundary.
Yes.
So you don't have, I mean, at the boundary, you don't have any black hole. So that black hole is not evaporating. This thing will evaporate through bulk Hawking radiation.
Normally, the plasma ball doesn't evaporate, and the reason I think is because you have a large system, you have a large number of degrees of freedom which are all entangled inside, and you have a very hard time to meet and quality confined degrees of freedom which you need to go outside. So that's the reason. But maybe here there is a similar system because you have a large CFP. I don't know if
there's some of this which is similar. Yeah, some of this which is similar. The plasma ball, the black hole, and the confining background, this would evaporate through bulk quantum effects, but that's suppressed. This is 1 over X suppressed. But the problem that we have here is that we have at the boundary, we have something that you would think it should radiate, and it doesn't seem to be radiating. Or at least it's not emitting radiation. Okay.
The only reason is that maybe the CFT has a huge amount of degrees of freedom, so there's a huge amount of degrees of freedom entangled with the black hole, which have a very hard time meeting and forming a deconfinement.
We're going to, I think strong coupling. Strong coupling is what's making empty space perfectly insulated. I will come back to this. But so we're revisiting the problem. So kind of a year or two ago, we thought that we would revisit this problem and changing a little bit the picture. So instead of considering the black holes in Poincare ADS, we make them, we consider them in global ADS, so our boundary is a sphere possibly with black holes. This is good because this gives you infrared regulation of effects. And we also found that the bulk dynamics that we get in this case is richer. So it's a better system than what people initially thought of a flat boundary, synthetic flat boundary. And then the other thing that we've changed is that in order to solve the dynamics, we're using something that's more recent, which is we're using these techniques of going to the large D limit, because this allows us to study horizon dynamics in a much simpler way, much more efficient way. So we don't have to run simulations to supercomputers. We can do them in our laptop and get at least the qualitative dynamics of the system. So static and dynamical problems using these large D methods are doable. So we applied these ideas first. We first did the thing without the brain. So we studied the dynamics and the phases of a conformal field theory in a fixed black hole background. So we don't have any brain here. This is a paper that appeared last year. The paper that's going to appear is changing this now to having dynamics on the boundary. So that's having a brain. Let me first begin with the first problem. So the simplest system that we start with, so we take global ADS, so we have a spherical boundary, And at the boundary, what we now have is going to be two black holes instead of one. Because that's a simple solution which does this. A sphere with two black holes at underdeveloped points. What is the solution, the bulk solution that describes this? Well, it's nothing but a black string that extends into the boundary. This solution is explicit, it's simple, you can write it. So this would be, if this were flat space, this would be just global ADS, but we can replace the flat space here with a black hole. This black. So what we have at the boundary is when the black string intersects the boundary, and we have one black hole on one side, and a black hole at another side. Okay. The geometry of the boundary is fixed. Well, in AES in general, what you want to do is to fix the boundary geometry and find what kind of configurations fill in that bulk. So there are other phases for black holes where you have two black holes at the boundary. One of them is the one that I just described, which sometimes it's called a uniform black string, or you can call it also a black panel. But you can also have configurations where you have black holes in droplet configurations. The boundaries are the same in that configuration, in this one, and also in a third one. You can also have what's called a fat funnel, where you can think of this as a large ADS black hole that's connected to the boundary through some thin tubes, through some funnels that intersect the boundary at black holes.
So, Roberto,
yes.
The previous solution, is that an exact solution of Lennon's equations in ADS?
So this one, the uniform black string, is an exact solution. The other ones are solutions that you have to find numerically. There's no exact solution for them. These solutions were constructed numerically as static configurations by Don Manuel and George Santos 3 years ago. And there are other possibilities. You can also have other configurations, but these are the main ones.
So they can work with it too, right?
In general, yes. Yes.
Do you need the supersymmetry, or is it, I mean, when you have these two guys here, and I guess it's difficult to bubbles which are not opposite, but just attractive collapse, I guess. Or...
Well, the boundary geometry is not dynamical.
Oh.
At this stage, later it can become dynamical, but in principle, this is not dynamical. These are black holes that are, and that those solutions are stable as far as. Well, these ones need not be stable.
The uniform black string, it's exact because it's that case where the Feldman dynamics function truncates.
You can say that.
Einstein and
you can say it that way. You can also say it basically in other ways. You can also say that it only excites the zero mode of the graviton bulk. The same thing. Yeah, the stress in the tensor is 0 up to a trace anomaly, which is what you were saying. So, I mean, when this black string, when it's thin enough, well, thin black strings, they want to pinch. That's what Gregory and Laplan discovered. So the thin black strings here are also active. If they are large, no, they don't. If they are large, they are kind of inside a box that's snug enough, and then they are not unstable. But this was this instability at the nearest level. This was discussed by William and Kang already also some time ago. So these are the static solutions. But we want to do also study more phases and in particular dynamics. For this, we've used this large effective theory that we began to develop a few years ago. It was also developed kind of in parallel by a group in India. The idea here, I'm going to give you a brief tour of how large T methods can help us here. The idea is the following. If you have a black hole and then you have a gravitational, the gravitational field of a black hole, when the number of dimensions grows very large, well, the potentials get very steep, which means that the gravitational dynamics gets localized very close to the horizon. Because you have a large gradient of the potential, so it gets localized very close to the horizon of the black hole. And this has some effects. One of them is that the radiation is suppressed. Black holes at large D, or gravitational radiation from a black hole system, is strongly suppressed. In fact, the suppression is non-perturbative in 1/D. So in the limit of infinite D, black holes that are moving around or which are evolving dynamically don't emit gravitational radiation, and this means that you have a huge simplification of the problem, because many of the problems that you find when you're doing dynamics with black holes is that you have radiation. But we're not interested in the radiation here. We're more interested in the dynamics, how the horizon evolves. And this is something that's well captured in the large D limit, but some effective theories that describe the slowest modes, something that we showed, that you can study the dynamics of the horizon in a way that's decoupled from the asymptotic region. And the way that this is done is by isolating fluctuations, modes of fluctuations of the horizon, and then in the infinite limit, you can separate high frequency modes from low frequency modes. You keep the low frequency modes, so the longest lived fluctuations of the horizon, and then you find an effective theory for them. So in the general case, for asymptotically flat black strings or black brains, you can reduce the full Einstein equations of a fluctuating brain or a fluctuating black string. You can reduce it to just equations like this one. You solve these equations, and then you solve in the full Einstein equations in this leading order limit, the latch D approximation. So you have two functions. One of them describes kind of the thickness of your brain, and the other one motion or velocities along the brain. I'm not going to do or to show you much more detail about the equations. The point to take here is that equations are simple.
So here, should I think of this as you integrating out some UV part of the geometry?
Yes.
And then defining some effective action close to the horizon that close to the horizon?
Yes. Yes.
So there's some diffusion equation for M, so
it's almost diffusion. So that's
diffusion, or I mean, is it with the wrong sign, or is
so the diffusion? No, it's a diffusion with the right sign, but there's also some instability. So there's diffusion, which is good, because and the horizons diffuse. So that's what this does. So this is the dissipative part of horizons. But then, in some cases, for black strings, for instance, you know that they are unstable. So here, what you have here is that, for instance, one problem that you can solve with these equations is the Gregor-Laflamme instability. If you do it for moderate D, this is similar to what the Lerner Pretorius did. This is what the Gregor-Laflamme instability does. If we use these equations of the large D effective theory, they do. Okay. So, and then, well, the fluid is unstable because of a sign in the equations, not the dissipative part, but another term.
Sorry, so how are you solving the moderate D? I thought you were using the large D limit to solve the equation.
So this is something that we use large D equation. So this is a solution, dynamical solution. The one above, it's my trickery.
6 months on the...
It's not, this I do in a fraction of a second.
So
but Lerner Pretorius did it with a 1 month in a supercomputer.
Well, you do it fast, but what do you do?
I can show you, but this is my sorcery, my private. Okay. But this is sorcery. Okay. This is not sorcery. This is a large D methods. Okay. So these equations.
Should I take it as what you expect?
So I mean, this is something that I saw as an illustration because I didn't want to take. I mean, there's a video. If you want to see the real thing in YouTube, you can see the video that Franz Pretorius put for the simulation, the supercomputer simulation. Now you see that the black holes that we have, they don't look spherical. They look like Gaussians. Well, the reason this is because in the large D limit, this is spheres. If you plot the area of a large D sphere is strongly localized near the equator. It's strongly localized. This is just so that if you think that these don't look like spheres, well, this is because I'm plotting the area, and the area of the sphere at large D, it's because of this, the area goes like this factor. So then this means that this is strongly localized near the equator. So that's just. But I mean, that was for black strings in a simple flat space. For black strings in ADS, we got something similar. The equations are similar. There are some new terms. This is in ADS. And the large limit, yes, please.
Excuse me, can I just thank you.
I talk too loud. So what we're doing is focusing a region, the region where the string is thinnest. That's where most of the dynamics is going on. So that's well, the equations here are describing that region. But these are the equations that we're going to solve, and that's much simpler than solving the full Einstein equation. This is something that you can do with MD solving the computers. Okay. So we solve these equations, and then we begin solving them for static configurations, and then we found the black string, that's just a uniform solution. We also found solution for black droplets, and also solution for fat funnels. So this is something that we found easily. But then we can also study dynamics of these objects. And these black strings, as I said, when they are thin enough, they are unstable. So what do these black strings do when they become unstable? They can do several things, but one interesting thing that they can do is that they can grow a blob in the middle. This is because you're having horizon generators coming in from the bulk, and then, well, they let, in this system, energy is not conserved, because the boundary conditions don't conserve energy. But what you have is the simulation, is a black string perturbed, and then it's growing. It grows so large, but that's the fat funnel. The dual view is that you're starting with these black holes at the boundary. So we're dualizing the bulk. These black holes are surrounded by some radiation, and then this radiation, the black holes are emitting radiation. The geometry is fixed, so the black holes, there's no back reaction, so the black holes can radiate as much energy as they want. What they do is they flood the entire spherical universe with radiation. So that's the picture, one of the black holes. It's radiating until you find that the black holes are in equilibrium with radiation. This black hole corresponds to thermal radiation at the boundary.
Do you find the equilibrium in the large picture also?
Yes.
Oh, okay.
Well, and there's a little caveat here because the black hole is becoming very large, but we can argue that we're going to.
Sorry, because the equations at large D are so simple, is it realistic to start picking up 1/d corrections and analyze that?
It can be done. Yeah, we've sometimes done that. Yeah, corrected. We've even sometimes gone to third or fourth order in the expansion. Then it's horrible, but with Mathematica you can do it. And the equations then take a few megabytes in a file, but they are analytic. The black droplets, on the other hand, they seem to be stable. You find them there, you perturb them, and they just relax back to. So, what you have in this case, you have a black hole surrounded by a halo, and the halo of CFT. The halo of the CFT is stable. So this is a black hole that's surrounded by thermal radiation, and this radiation is not going out to infinity. So this was the puzzle, that these things exist. This is the large diversion of the results of Pau and Toby.
Is it clear that the stability conditions that you derive are not artifacts of large D? That's something that looks stable at large D could not be unstable.
Well, the thing is that this is also found at finite D.
Okay.
And we can, I think that the result, could be that including corrections, but that doesn't seem to be the case because already at finite D they were found. So now we want to make, so far our black holes at the boundary are not dynamical, they are fixed backgrounds. Now we want to make them dynamical because we want these black holes to see whether they evaporate. So what we do is we change the picture now. We introduce a brain, that's the green line, that's the brain. So we have to modify our equations and put boundary conditions at some finite distance into the bulk. And the boundary conditions that we have to introduce are very simple. So the problem is, for solving the equations in your computer, it's almost the same. Because what you're just doing is changing one boundary condition, putting essentially a Neumann boundary condition at some finite distance. And then you can take these equations and again solve them. And when we solve them, well, first solution, the simplest one, is just the uniform solution. You have just a constant profile for the energy density. So what this describes, the case that you have two brains, what this describes is a configuration where you have two black holes, one on each of the brains. And then we have this system, there's no CFT, there's no CFT excited here.
Do the brains have a tension or
the brains have a tension?
So they have something to keep them from regular flaming themselves?
No, these brains, the brains are not black brains. The brains are just a domain wall. It's like a Randall syndrome brain. They are not black brains. So I draw them green because they are not black. Sorry.
And they are compact, like they are in CR.
Well, here they can be, here they are ADS, the geometry on each brain. Here it's ADS. You see that they go up to the asymptotic boundary, so they are infinite. But the entire system, it's conformally equivalent to a sphere. Well, at least when you put it at the boundary. Otherwise, yeah, it's just it's a half ADS space, or topologically, it's a sphere. The green surface, it's a sphere, where one half is some ADS swap.
Sphere time. Sphere times time.
Oh, yeah, it's always time. But in this configuration, this is static. So time is just continuous on this.
The gray area still has some ideas, or you have?
No, the gray area is what's removed. Yeah. So here, yeah, let me get back here. So what I do when I put the brain, I remove the rest, and this could be an end of the wall brain, or I could paste a symmetric copy, and then I could do a two-sided brain with all of a boundary dimensions. So that's the gray area is the gray region. Thank you. That's removed. What I keep is the black, the white part of the bulk. Okay. Is it clear? Am I going too fast? So we have this configuration, but we can also construct, by solving the equations, we found a solution that has one Gaussian localized at one end, another Gaussian localized at the other end. So we have two droplets.
So the brains are fixed at infinity in some form.
The brains are fixed at finite distance. So here, this is from finite distance, what they are fixed.
Okay, and at infinity, it does not do the same because of the idea.
At infinity here, I mean, this part, I mean, the large D methods, they focus on this region over here. Okay, so this is, you don't really see that it's going to infinity close to the boundary. So these are some of the static phases. There are other static phases. We can also construct droplets. So here you have one droplet, but then you also have a droplet that's kind of moved a little bit off into the bulk, and even higher one. So these are excited states. So you have here a black hole. So here you have the black hole. This the projection or the point where this Gaussian cuts the brain. This is a horizon on the brain. Then the rest, this is bulk. So here you have a black hole. Then the bulk that corresponds to having some radiation at the boundary. Here you have more radiation at the boundary. You have a smaller black hole surrounded by a halo of radiation. And here you have other black holes which are surrounded by funnier halos of radiation. So you have the black hole, and then you have one configuration of the CFT around it. Then you have another configuration of the CFT which is larger, this one. It's a larger halo. And there are even larger halos around the black hole.
So any blob in the bulk, any blob which you get in the bulk far away from the boundary, it's a halo on the boundary.
It's a halo.
It's from distance
Yes,
away.
exactly. Yeah, that's because whenever you have a horizon in the bulk, that translates into the boundary as some thermal state. And this thermal state, in this case, is localized around the black hole that you have over here. So you have this, and then you also have the bulk black hole, which corresponds to a thermal state at the boundary on the brains. So this black hole is full in the bulk. You don't have any black hole at the boundary, but this black hole in the bulk, what do black holes in the bulk do? Well, they correspond to thermal states of the CFT at the boundary.
So technically what you're doing is solving this pair of coupled equations that you were showing on the previous slide.
Yes.
So these are profiles for which of these functions?
So this is just the density profile, the M, which gives you the
thickness.
Yeah, the thickness. It's the, I mean, so this is M, this is the thickness of the profile, the velocity, and also the momentum, we could also plot, but it's less informal.
But they are the static solutions, right?
These are static solutions. Yeah, I mean, that P is a combination of pressure and momentum. So it's not really zero here because there's some pressure here, but that's a small technical detail.
So these are solutions where you set all time derivatives in the previous equation to zero.
Exactly. So you take these equations, you set time derivatives to zero, you get a relatively simple set of equations, you impose these boundary conditions, and then when you solve them, you cannot solve them in general analytically, but numerically, this is a very simple shooting problem.
And so then in principle, you can still use the same equations in order to perturb around the static solutions.
And you can even do things which are not perturbations. You can do nonlinear, transfer these equations nonlinear. But you can perturb them and then study the stability.
Sorry, Roberto. You refer always to the shifting on the boundary.
Yes.
The boundary are really the two dots up and down.
No, I'm not taking the double holography, the second step in double holography. So what I'm taking is what people, you're familiar with Katz-Randall, of course. So you know that there's three different pictures. The full bulk picture, where everything is just the gravity. Then there's also the picture where you dualize the bulk, but you keep this boundary, which is sometimes called the intermediate boundary, or the intermediate picture. And then there's a third picture where you dualize the brain, which is a gravitative system, and then you dualize it to a defect. Okay, so in that case, what you would have is a CFT in one less dimension. I'm taking the intermediate picture, what I'm dualizing is just the CFT in the bulk, but not dualizing the brains. The brains are dynamical, so what I get is the classical gravity in the bulk, that's CFT at the boundary, and part of the boundary is dynamical. In this case, all of the boundary is dynamical. Here you have a dynamical geometry, where you have a black hole coupled to a non-dynamical system. Yeah, everything is
so for you, the CFT, so it's a cutoff CFT.
It's a cutoff CFT, coupled,
massive gravity.
Yeah, coupled to massive gravity, yes. Massive gravity in the brains, yes. So that was static. So now we're going to do dynamics, which is, after all, what...
Sorry, it's a naive question because I don't know that well. What is the relation with the coupling in that case? Because I see two CFTs possible in terms of strong coupling, weak coupling. What is classical gravity describing in terms of quantum?
So, I mean, you're talking, so the CFT that lives on the brain, that's just the usual, I mean, if this were, say, in ABS5, that would be super young mills, because for super young mills. You dualize it further, then that's going to be a theory, then you have to provide some realization of what is the defect of your young mills.
So the intermediate step is really classical gravity coupled to strongly coupled large and yes, strong coupling.
That's right.
So your constructions are not addressing this comment or complaint that Karsh has, that
the massive gravity is...
and it's unclear to what extent this will carry over to massless gravity.
I mean, there's some things, for some things I think that there may be some caveats to what one, but for what we're saying, I don't think that's relevant, because what we're after more is the dynamics of the coupled system. I don't think that the massive gravity here is going to be a very important problem. What he was, him and Suzuki and others were saying that the massive gravity may have something to do with the appearance or not appearance of islands. We're not talking about islands. I don't think that that's a big issue. I mean, I think it's less of an issue that they say. But in any case, I don't think it's relevant for what to do.
The massive gravity is where?
The massive gravity is on the brain.
Because I thought it was somehow connected, sorry, I thought it was somehow connected to the non-conservation of the bulk stress tensor.
Yes.
So I thought that you had some sort of energy going from the bulk of the
you can have
to the boundaries. That one is also massive?
No, so I mean, what you have is that there can be flows of energy from the brain into the bulk. So this system, and in this case, the stress tensor over here, then it's not conserved, and that is related to the appearance of a massive graviton. That's something that for us, because for us, what we're interested in is mostly dynamics over here, not dynamics up here. So that's one of the reasons that I think that the massive graviton is something that you see when you're far, when you're close to something that appears at large distances. So since we're focusing on a region where, for us, the interesting dynamics is happening near the center. The effects of the massive graviton, I think that they are not at all important for us. So because I mean, the massive graviton is something that appears at the large distances. It's a small mass in general. It's a long distance infrared effect. It's due to the interaction of this brain with the bath, if you want, and that's something that for us it's not. Any more questions? So, well, now that we have the setup, we begin to play with it. And the first thing that we can do is, well, simplest thing is we have a blob of radiation, and then that's gravitating, and then we let this blob of radiation collapse and form a black hole. So what we have is, when we have a black hole in the bulk, this corresponds to radiation, a blob of radiation at the boundary. Now I throw this black hole to the boundary. What does the dual picture do? What does the radiation do? The black hole fall into the bulk. was radiation expanding. A black hole, you throw it to the boundary, and then that's radiation collapsing. But now this radiation is collapsing into a system where you have dynamical gravity. What does collapsing radiation do when there's gravity? Well, it forms a black hole. What does this black hole, what do you want this black hole to do when you throw it to the boundary? Throw it to the boundary, it hits the boundary, and then it creates a black hole at the ground boundary. So this is what we do here. That's it. Okay, so this, we threw a black hole in the bulk, we threw it to the boundary, and then it sticks there. And if you didn't see it moving for some seconds, it's because this is stable. The simulation was still running. So what we're doing is we're throwing the black hole to the boundary. Now you have this horizon at the boundary. We've done holographically collapse of quantum CFT radiation to form a black hole. So this is the formation of the black hole, but we're interested not only in the formation, we're interested it was foreplay. We want evaporation. So
why this guy did not evaporate? It's negligible, or it's,
because this is a droplet on the brain, and that doesn't evaporate. I'll get because now what I'm going to do is show you some pictures, and then I will tell you what's the interpretation. We begin with this black string.
It's also a matter of timing, right? Because the black hole formation has a very short time. The time you throw the black hole from the bulk, the boundary, it takes some short time, and then we have the radiation collapsing from the black hole. There's the black hole, there's the horizon crossing time. So black hole formation takes place in a very short time. So the evaporation, if you want to do it properly,
that's why I was asking. It was negligible here because
at the evaporation here, you have a large number of CFT fields, CFT degrees of freedom that you can evaporate into. So that makes the process of evaporation, it would make it also the same order.
But are you also pumping energy or not? Because when you have this tsunami, you're pumping energy from the boundary.
Here we're not pumping energy. Here our boundary conditions are energy conserving.
Okay.
Because our boundary.
The original tsunami was really pumping energy from the boundary, and we just pump energy and then
but here now we're going to see it's going to be a finite tsunami because here we're conserving energy. So here we have the black string. We let it run. Good morning. So now what we have is we have the tsunami. So we have things flowing to the bulk, but now our boundary conditions are energy preserving. So what happens is that the black hole at the boundary, let me run it again. So this is shrinking. The black holes are evaporating the boundary. Here we kick the system in a different way. So one black hole is shrinking and the other one is growing. So one of them is evaporating into the other. I will tell you later what's the proper way of thinking about it. But then we can also have something else. We can have a black hole, a large black hole, a relatively large black hole in the bulk, and a smaller black hole at the boundary. Something like this. So now the black hole at the boundary has evaporated into the black hole in the bulk. Okay. And this is wobbling just because of conservation of momentum. So those two were simulations that we ran. Let me now explain how we interpret them. What does, because we've seen that the dual, holographic dual of evaporation is possible, which is something that was thought that it wouldn't occur. So what we have is that the black hole evaporates, the black hole in the brain evaporates by funneling radiation, sending radiation into some colder horizon in the bulk, or on some other brain. The way that this, and the basic rule governing this is that hot radiates into cold. That's simple. Everyone knows this. So this is what you have to keep in mind. Now, you also need your black hole at the boundary to be connected with some funnel to something in the bulk. This is what you don't have in the droplet. The droplet is disconnected from the deconfined degrees of freedom. You're radiating into deconfined degrees of freedom. So what this needs is that you need the black hole on the brain to be connected to some black funnel, to some horizon, to another horizon in the bulk. Okay. So this is why the droplet doesn't evaporate, because the droplet is not connected to any colder system that it can evaporate in. It's disconnected from all the deconfined degrees of freedom that you have in your CFT.
if you're only on the boundary, what it is like stimulation of evaporation through another radiation. Like if you're only in the boundary, I don't know that there is something inside. What your black hole inside is just radiation.
So you wouldn't. It's difficult to see. I mean, from the point of view of the boundary, whether you have this funnel. This funnel is something that, from the point of view of the CFT, is something that's connecting low energy degrees of freedom to high energy degrees of freedom. And that's something that I think that from the quantum field theory point of view is very difficult to understand. At least I don't know of any model. I know how to
it's still some interaction between confined and unconfined degrees of freedom, which does happen, you know.
Yes.
The solution exists, so the interaction must happen, you know.
Yeah, but you see it when you understand. Yeah.
When you have this funnel, you know, you ping it from the boundary, it goes to the bulk and goes back. So, you know, you put some energy in the global energy of freedom, and you know, it goes to the deconfined ones and goes back.
I don't understand it just from the boundary.
This is something that we understand from the bulk. I don't think that we have a good understanding of these funnels from boundary.
The node evaporation from the boundary perspective, I think it makes sense because then you have a confined theory with the mass gap. So then you basically have a very cold black hole, you know, there's a mass gap, and that's going to set off the radiation. So, you know, essentially the energy of total radiation is below the mass gap. So you don't excite. You don't have degrees of freedom because, you know, the safety zone is here. You don't have degrees of freedom with, I mean, if the black hole is cold enough, then, you know, the degrees of freedom are massive, so then you just don't decide.
Maybe we can, I'm going to give a few more examples and we can come back to this issue because it's an important issue, which I don't think it's well understood from the CFT point of view.
Time-wise,
I'm almost running, yes. So I'll be in a few minutes. So in order to understand this, what we have is first, we have ADS, we can have large black holes. Large black holes are hotter the bigger they are. And small black holes which are smaller than the ADS radius, they are more like asymptotic black holes. These are colder the bigger they are. That's important for what we want to see. So in some, this is one of the, I'm going to show you again, one of the simulations that I showed you before. What's something that I didn't say is that in this case, we're considering a thin string, which means that on the boundary we have a small black hole, and this is a black hole that's hotter the smaller it is, just like black holes in a synthetic flat space. So we're perturbing it, we're introducing a perturbation that makes it hotter here and colder here. Because here it's bigger, it's colder. Here it's smaller, it's hotter. So what is this going to do? It's going to emit radiation from the hotter to the colder part of the system. And that's what the simulation does. We have radiation from hotter to colder until it fully evaporates.
When you have this funnel, it's a solution. The temperature of the horizon should be the same.
Yes, but that's why I perturb it. I introduce a perturbation. Now I introduce another perturbation.
So these funnels, they're always going to be unstable, basically.
These funnels, when they are thin enough, they are always unstable. And then you can kick different instabilities. And one of the instabilities is this one, another instability. You can perturb it in such a way that this is hotter and that's colder. So in this case, what we have is that the hot radiates into the cold. And then in this other case, what you have is a black hole that's large in the bulk, but it's large in the regime of small ADS black hole. So this is colder, and this is hotter.
But the starting point is just a solution. So
it's not a solution.
It's not a solution.
It's just some initial data.
It's initial data. Okay.
In this case, we don't need to perturb it. It's something that we made up. We can do that. We can choose our initial data. So what we have is here this black hole, which is hotter, which is going to evaporate into a colder bath in the bulk. And that's what it does. It's evaporating until you find this one. Okay. So that's the idea. You can also have the reverse. You can have a hotter black hole in the bulk, pumping energy. In this case, what you have is that the black hole is surrounded by it's cold, it's surrounded by a hot bath, and it absorbs the bath. And then, well, black droplets, they are stable, they don't evaporate. The empty bulk acts as a perfect insulator. This is what we're saying. Here, these black holes, they cannot evaporate into each other because there's no deconfined degrees of freedom connecting them. There's no bulk horizon connecting them. So, as I say, this is because the order n squared degrees of freedom are not accessible. Because we say this is, you should somehow trigger some deconfinement in order to to let it evaporate. And that, if you have a bulk black hole, then those are these deconfined degrees of freedom. This is an infinite coupling effect, probably, infinite strongly coupled effect. And then, well, of course, they would emit radiation if you allow for quantum effects in the bulk, but that's suppressed. That's something that we don't see in our approximation. Let me come to the end of the talk. So what we've seen is that we can have a classicalization of Hawking evaporation. There is this phenomenon that I mentioned that I want to investigate also with Maria, that the endpoint of the Hawking evaporation here seems to be essentially the same as the endpoint of the Gregor-Lagrange instability, which is a classical naked singularity that you find, in this case related to a quantum naked singularity. And then there's also a question of whether this can be used for studying processes in black hole formation, because we're following the entire evaporation of the black hole using classical methods. So the conclusions, and here, is that first of all, we've seen that it's possible to have a black hole evaporating into the bulk, and the process, some classical phenomenon that describes the quantum radiation of CFT coupled to the black hole with back reactions. There are differences relative than what we find, or what you find when you're studying the free Hawking radiation. This is the thing that we were not sufficiently aware of 20 years ago. Now we've grown older and wiser, and yeah, we think that that infinite coupling and infinite end effects are crucial for capturing what is the evolution of the system. Because there are these things like these stable hot CFT halos around black holes, but this is an effect of infinite strong coupling. The empty bulk is infinitely, it's a perfect insulator. And the basic rule is that we verified is that we always have that a black hole connected, a black hole that's in some part of your system connected to another black hole that's colder, so the hot goes into cold. That's the thumb rule for how the evolution is going to go, which is a very simple thumb rule. Okay. So here, I'll stop and thank you for your attention.
What I suggest we do.
Let me just before an announcement. For those of you who know about our Benasque workshop, next year we will have it. This is a picture that I took last July, so it's still there. In the lake.
I like the cafeteria though.
So yeah, so that's my part. Thank you.
Maybe we can take a few questions that are going to be recorded and turn off the recording, especially if like junior people want to ask questions. I think we've had many questions from more senior people, but not so many from
okay, yeah, let's do that. Yeah, Yosif, you can handle that.
I think
Junior, Yosif is
I'm very junior. Like,
ask your question.
Okay. No, I think this panel connected to the bulk. I think what you're doing, you're making next to the black hole, you're putting the black hole in a huge bulk of deconfined degrees of freedom.
Yes.
And then the Hawking process, because of the curvature, the tiny curvature, just because you have a huge amount of deconfined degrees of freedom working around, you just excite them. You have all the n squared degrees of freedom, and then because of the curvature, you just excite a huge amount of them as Hawking quanta. They just evaporate very fast, and that's why this effect, and that's why the effect is classical.
Yes.
You have the evaporation takes place in a small time.
Yes.
And the reason why the time is small, normally black hole evaporates the time over the cube. Here, the black hole evaporates the time over the M. But I think the point is you have n squared degrees of freedom because of the deconfined. And so you're basically when you make this funnel, you're putting the black hole in some atmosphere of n squared degrees of freedom, which are all exciting. Yes. And then the black hole excites one of them, and then it just speeds all the energy out.
Exactly.
I think that's why you have, if you don't have the funnel, then you put the black hole in a confined phase. So then in the confined vacuum, there's only one, there are no degrees of freedom there, and then the black hole.
You can only see that by including 1/n corrections. That's very slow.
Yes.
It's not like it's strictly zero, then it's like the standard Hawking radiation, and you just don't see it.
We don't see it when we're just in the classical bulk. If you include 1/n corrections, then you would see, and then it would be slow. Here, as Joseph was saying, what you have. You have access to a large number of degrees of freedom, order n squared. So your evaporation goes very quickly because you can evaporate in n² channels, in n² fields, and that's what makes this process so fast. Whereas if you don't have access to these n² degrees of freedom, then it goes slow.
Other questions? Maybe we can stop the recording. Okay.